So in 1994, when we embarked on our mission to measure supernovae back in time, we were not the only ones with this good idea. Rather, there was a team that had been looking for distant stars since the late 1980s based out of Berkeley. And so two teams ended up competing to measure the universe's past. One led by me, the high redshift supernova team. We were made up of people who typically studied supernovae. And a team led by Saul Perlmutter called the Supernova Cosmology Project. They were based out of particle physics, and they had been looking for the distant supernovae for the past several years. And so this was really quite a competitive team, and you can see Saul and I were often, poised as boxers trying to punch each other out to get and figure out the ultimate fate of the universe first. But we had quite a friendly time amongst all the competition. But it was not easy work because it was hard to find these exploding stars. Here is a picture that we would take of a piece of the sky. There's several thousand galaxies in here. We would take about 1,000 of these images a night. This was back when we had very slow computers and very small hard drives. And so the challenge was to find the needle in the haystack. We would take about 50 gigabytes of data back in the days when we only had 1 gigabyte hard drives. And so in this haystack, there is a little diamond in the rough, a supernova. It turns out to be that little guy. And the way we knew that was a supernova was by taking two images. We would go through, take an image, and then come back and look at the same piece of sky a few weeks later. My job was to write the software that did all this as automatically as possible. In this image, you can see that nothing on the 4th of April became something on the 28th of April. This object was more than 5 billion light years in distance, so it exploded before the Earth was formed. Now, my software was there to find things, but truth be said, it needed a lot of help. So everyone on the team would go through these very long exercises to find the supernovae. And we had a student, in this case Sarab Jha, we had a faculty member, Peter Garnovich, and we had a full professor in the form of John Tonry, all members of my team, all doing the same thing, sifting through this data, looking for the exploding stars that my software put out as possible candidates. After 3 very hard years of work, Adam Rees, one of the youngest people on our team, was analyzing the data. And as we worked through the team with Adam, we found something remarkable. We found the universe was expanding, it seems, slower in the past, and it actually sped up. So what this diagram shows is our data from 1998. You go through and you measure the scale factor in the form of the redshift, this direction, and you measure the average expansion rate to the object in this direction. That's really a measure of the distance and the redshift. Each supernova has uncertainty, and so you don't know exactly the answer from a supernova because they're not perfectly calibrated. And so these error bars represent where 68% of the time the correct answer lies. So you sort of have to make a judgment with your eyes as an average. We do have statistical techniques to do this. So you can see in the nearby universe, these are objects taken by our Chilean colleagues who are also members of the team. You can't tell what's going on. But these objects, well, you can note that not a single one of them is consistent with the part of the diagram where the universe is slowing down so fast that gravity wins and the universe eventually stops expanding. But on average, they don't lie in the yellow part of the diagram either, where the universe is slowing down. Rather, they lie in the part of the diagram we weren't really expecting anything, where the universe was accelerating over time. That is, it was speeding up, expanding slower in the past and speeding up over the last 5 billion years or so. What a surprise.